Hey, have you ever felt the need to do variational quantum Monte Carlo simulations? Well, today's your lucky day. Never fear, the physicists are here. In just 4 easy steps, we're going to show you how to do variational quantum Monte Carlo simulations and apply it to the helium atom. Physicists study what happens at the subatomic level all the way to the scale of the universe. We aim to form a mathematical description of the world called a model. This can help us to understand physical phenomena. Known as the father of modern science, Isaac Newton pioneered his theory of classical mechanics. This implies a deterministic view of the world. It says that if we know the state of everything at this moment, we should be able to predict what happens in the future. As beautiful and logical this sounds, this isn't true, and it breaks down at the subatomic levels. Quantum mechanics, the set of laws which govern interactions at the atomic scales, replaces classical mechanics at this level. This is where Heisenberg's uncertainty principle, Schrödinger's equation, and wave-particle duality takes place. Heisenberg's uncertainty principle is basically to do with the wave nature of particles. For example, electrons in an atom do not orbit the nucleus like planets orbiting the sun, because that would violate Heisenberg's principle. Instead, we introduce something called an orbital and state that there's a certain probability of finding the electron in this space.
With normalization, the electron's wave function squared is basically a PDF stating the probability of finding the electron in this region.
Physicists have calculated these wave functions for simple cases such as the hydrogen atom, but for the next atom in the periodic table, helium, it's ridiculously difficult to solve due to the complexity induced by electron-electron repulsion. Now we have a grip on quantum mechanics. Let us consider one of its applications. We will look at the variational method, which allows us to determine the ground state energy of helium. Knowing this energy is important because it allows us to compare with the experimental ionization energy, so that we can see if our understanding of the world is correct. The variational method is true because that the Schrödinger equation is an eigenvalue equation made up of the operator, the Hamiltonian, the Schral wave function, and the energy, which is the eigenvalue. Assuming that the nucleus is way heavier than the electrons, the Hamiltonian for the hydrogen and helium case are written as such. They are very similar and are related by their total energies. As mentioned, the Schrödinger equation is difficult to solve for helium, and we must use an educated guess of the Schral wave function form. The best form obeys certain cusp conditions and some symmetries or anti-symmetries. However, there also are numerical constants to be determined in the problem. The variational principle states that the energy obtained by an approximate Schral function is always too high. Thus, the best Schral function will give the lowest energy and will eventually approach the ground state energy. Using some maths, the problem of finding the energy in the Schrödinger equation is reduced to finding the minimum value integral, called the variation integral. In precise terms, we would like to find the variational parameters that minimize the variational integral. In the modern day, problems like these can be fed into a computer, where we input variation parameters, compute the integral, and measure the energy that it outputs. My colleague and I have been working very hard to develop a code ecosystem that can compute these monstrous integral optimizations using numerical algorithms.
So let's say we have a one-dimensional function, but it is a black box, which means that if you give it some ingredients, it will give you a result, but you have no idea how it arrived at those results in the first place. How then would you calculate its integral?
Oh, a Riemann sum.
Exactly. Since we can't apply our beloved analytic integration techniques on our black box, we have to resort to drawing thin trapeziums under the curve and then adding the areas up. This is called the Riemann sum. It is simply an approximation of the area under the curve. Clearly, since the function doesn't change and the area of the trapezium is well known, every time you run this method, you'll get the exact same result. This is called a deterministic method. That sounds fantastic, but let's see what happens when I dial up the dimensionality from 1 all the way to
7 hours later.
As we discovered, such deterministic algorithms suffer from something called the Ursula dimensionality due to their geometric nature. This means that their computational complexity increases exponentially as you increase the dimensions. But never fear, the code monkeys are here. There is actually an alternative to tackling high dimensionality integrals, and those are called Monte Carlo methods. Basically, Monte Carlo integration involves the use of random numbers, which is actually how it got its name, since Monte Carlo is where you can find the world-famous Plage du Casino. So let's go through the basic operating principles of Monte Carlo integration. We consider a one-dimensional function called f of x. So the area under f of x is actually the same as a rectangular function with a length of b and a height of the average value of f of x, which we will call the mean. Finding the area of the rectangle is easy peasy, it's just the mean multiplied by b. So would you agree with me that the mean would literally be every single value of f of x averaged? But since f of x is continuous and it's a little bit hard to average an infinite number of points in a computer, what we will do instead is to take 1,000 random sample draws that are equally distributed along x and average those instead. It turns out that with large numbers, this is actually a good enough method to get an approximate of the mean. Of course, if we randomly draw 1,000 samples every single time, we will find that our mean value changes every single time. This variance can actually be represented very nicely by a Gaussian distribution, according to the central limit theorem. We can therefore report our mean result with an uncertainty that is equal to the standard deviation of the Gaussian distribution. So here's the thing, the beauty of the Monte Carlo method is that it is easy to draw random samples in low dimension as well as high dimensions, and therefore Monte Carlo methods avoid the curse of dimensionality. That being said, Monte Carlo integration is extremely diversified and has many popular forms. So for quVario, we offer not one, not two, but 3 different forms of algorithms for your integration pleasure. They are easy to use, completely general in terms of dimensionality, and are 100% bug-free, I think. Right? They're bug-free, right? For those who like things simple, we offer the uniform Monte Carlo method, which is simply the generalized version of my previous example. While this is the easiest to implement, it can also generate huge uncertainties because you might undersample regions of the graph that contribute more to the mean. So we need a smarter way to sample from our graph, which brings us to the second algorithm, which is called Metropolis-Hastings algorithm. It uses a clever trick where you break a function down into the product of a probability distribution and an auxiliary function of interest. The next part is to introduce something called walkers, which are sequences of sampled points. However, we only accept sample points if they are converging towards regions of high probability. We can see this probability function as a kind of measure of how useful certain regions of your space are. So by sending walkers, you can efficiently pick samples for calculations. If you're still unimpressed, we offer you the most advanced of our algorithms called Vegas. Vegas works by taking an initial sample of your integration space before chopping up this space into strategic regions called stratas. If your region is of high importance to the calculation, you would have a strata that has a higher sampling density. At the same time, within each strata, Vegas would choose a suitable probability distribution to pick sample points from other than a uniform distribution. Of course, when using our product, please make sure to customize it according to your personal preferences, such as the integration bounds and how many initial points to discard in case, say, your walkers have not reached an equilibrium distribution yet. Needless to say, we have done extensive alpha testing of our product with our customers. So here are some FAQs.
Which method gives the best accuracy, variance, and time?
For our uniform integrator, we find that for the helium 6-dimensional problem, it just doesn't cut it due to the nature of our quantum system. So it really is a close fight between Metropolis and Vegas, where Vegas will tend to be more accurate by giving more correct significant figures and have smaller variances. But Metropolis tends to be faster for our current implementation. How many iterations is enough?
Increasing the number of iterations clearly allows our integrator to converge to the correct literature value more easily. Something interesting is that the average optimized energy is lower for lower number of iterations, but it doesn't mean that we have broken physics. This is because that energies at lower iterations have high variance, and our optimization algorithm is systematically biased towards these smaller energies. We would recommend choosing an intermediate number of iterations, such as 5 times 10 to the 5 iterations to balance this effect out. What even is a good bound for a quantum system integration?
So for a quantum system, the idea of integration bounds is quite important in terms of improving our computational efficiency. If your probability distribution looks a bit like a Gaussian distribution, then you'll find that after increasing your probability from encompassing 97.5% of the states to say 99.9, your final value won't really improve. The Metropolis algorithm, on the other hand, doesn't require you to input a bounds at all.
To improve, we can do more iterations, do it on another atom, on excited states of helium. It's pretty exciting. Also, we will look at whole new optimization methods. In this video, we've gone through quantum mechanics, a variation method, numerical integration techniques. We've also evaluated our results. Thank you, hope you've enjoyed.
Bye.